Okay, so in this week, we're going to be talking about the very popular EM algorithm or the expectation maximization algorithm. This is one of the most popular optimization algorithms in statistics. And we introduce it at this stage, mainly, primarily because it turns out to be an important application of the algorithm we did in the previous week. And we'll sort of look into that connection a little bit in this video as well. Now, the premise of the EM algorithm can be a little confusing sometimes because it involves sort of underlying imagination to some extent. And so I'm going to ask you to sort of stay with me through the course of this video and sort of try and really listen to what we're trying to go through. Okay. So our objective is still the same in the sense that we're interested in obtaining theta star, which is the argument that maximizes f of theta. So that premise holds still. But so far in our optimization problems, we have looked at objective functions in general being denoted as some f of theta. Now, for the purposes of the EM algorithm, we will now basically assume that the objective function is in fact arising from the log likelihood having observed some data. Now, this assumption we sort of still had in all of our previous videos as well on optimization, in the sense that f of theta was typically often constructed just from the likelihood. However, when we did ridge regression or bridge regression, we actually looked at the penalized likelihood or the negative likelihood penalized by some function. So here we're just assuming that our objective function is going to be arising from a log likelihood. Now, with that assumption, if we have a parameter vector theta, so this is multidimensional, so theta is a vector. Suppose that I observe x1 up to xn from some distribution such that the joint density is f of bold x theta. Now here bold x theta is small x1, small x2, small xn, right? So for each capital x1, xi, there's a small xi that I observe, right? And that I denote by bold x, right? So we have the joint distribution, the joint density function of f of x given theta. And what we're interested in is maximizing the log likelihood or the log L theta given x, L theta given x, which is equal to log of f of x given theta. Okay? Now, if I do have independent observations, then this becomes log of product of f of xi given theta, I going from 1 to n. Right? If I have independence, which I'll assume most often that I have independence, but I need not have independence. I don't want to assume that in my notation. Now, suppose, and this is really where it gets a little complicated, but suppose for some reason, and you will see why this will happen later, we assume that there are hidden data z1 up to zn. Okay, so there are some hidden data that we will not observe. And those I denote by bold z, which is combined of observations z1 up to zn. Now here m may not be the same as n, the original size of the data observed. Okay, they may not be and they might be. Okay, now these bold z data, these m observations, we actually do not observe, and hence they are termed as hidden or latent observations or latent data or hidden data. Okay. Now, what is a good example we'll actually see in the next video, but the complete data of the observed data and the hidden data is bold x and bold z together. The observed data is just bold x. So accordingly, the observed likelihood is f of x given theta, because we observe x, so the observed likelihood is f of x given theta. But the complete likelihood, if we had observed both z and x, is f of x comma z given theta. Right? So these are the two distinctions between the observed likelihood and the complete likelihood. Okay. So this one we actually don't observe. Okay. Now further, if I use the relationship between the joint distribution and the marginal distribution of joint and marginal random variables, we can then write the marginal distribution of x given theta as the integral of the joint distribution, integral with respect to z, right? So I want to integrate out z. Now here's where there's a little bit of notational annoyance, because I am saying integral dvz, which denotes either integration or summation, depending on whether I have a continuous random variable for z or a discrete random variable for z, right? Because if I have a discrete random variable, then integrating out means summing out. And if I have a continuous random variable, then I actually do have an integral. Okay? So if I have discrete random variable, so z is discrete, then f of x given z is equal to summation over all possible values of z, f of x z given theta. Right? So the integral gets replaced by summation. And we'll see an example of both summation and integral in this video. So this dvz is just a short way of saying that this integral can be an integration or a summation based on whether z is continuous or discrete. Now, our goal is to obtain the maximum likelihood estimate of theta based on the observed likelihood. Okay, so over here, I am basing this on the observed likelihood only. So our goal is still the same. I want to obtain this thing, the maximizer of this part here, right? What is the theta that maximizes the log of the observed likelihood? However, note that we can write our objective function, which is the log of the observed likelihood, the log of this likelihood, as L theta being log of my observed likelihood, which is nothing but log of this integral of the joint likelihood f of x comma z given theta, right? So this is your joint likelihood or joint distribution coming from the complete data likelihood. Now again, I reiterate, this seems all quite arbitrary, and if you're confused, it's okay. It's expected for some confusion to be there, because the whole premise is that z makes no sense. Z is latent. Z is assumed to be some hidden data that we have not observed. So if we have not observed it, why are we using it? Right? And it'll be clear as we move on to the examples as to why it is actually useful. So if you're confused, just hold on to the confusion for maybe one video, and in the next one, I think it will be clear. Now, what the EM algorithm does is, instead of solving this objective function, it maximizes this objective function. Now, these are the same objective functions, but looking at this objective function instead of this form of that objective function turns out to be easier to solve using the EM algorithm. Okay, so the EM algorithm will produce iterates theta k, just like Newton-Raphson and gradient descent and MM algorithm. It will produce iterates theta k in order to solve the above maximization problem. Writing the target objective function in this form allows us to do optimization using this EM algorithm via two steps. The EM algorithm iterates through an E step, which is an expectation step, and an M step, which is a maximization step. Okay, so how do these steps work? So first, consider that you choose a starting value theta 0. Okay, so if you choose a theta 0, then that can give you theta 1, theta 2, theta up to so on. Then for any iteration k plus 1, given iteration k, so let me write, given theta k, first I do my E step, which is compute the expectation of the complete expected log likelihood. Okay, so I obtain my q theta given theta k. What is theta given theta k? It is the expectation with respect to the distribution of z given x. What is z given x? It is the distribution of the unobserved data given the observed data. Now we'll get to what this expectation looks like. But it's the expectation of log of the joint joint likelihood or the complete log likelihood. So this thing, let me write over here, this thing is the complete log likelihood. Okay. And this thing over here says, well, expectation of the complete log likelihood given the vector of observations x and the current iteration theta. So this indicates conditional on the observed data x and the current value of theta k. Okay, and we'll take a closer look at what Q looks like in just maybe a few minutes. Okay, so again, Q theta given theta k is a function as a function is a function with respect to theta and changes with every iteration. So the shape and style of the function changes based on our previous iteration, and it is a function with respect to theta. Okay. Now, what is it? It is again the expectation of the log of the joint distribution or the log of the complete likelihood given the current data and theta k, right? The current value. Right? So expectation is computed with respect to the conditional distribution of z given x equals small x, our data observed, and the current rate theta. Now, whatever we get from this step is a function of theta given the current value of theta k. So that means for different values of theta, this takes different values. And what the M step does is it says, okay, find the value where this Q is maximized. And that is theta k plus 1. So theta k plus 1 is the argument that maximizes Q theta given theta k. When the update size is small, then we can essentially stop our process. When the update size is sufficiently small. Now let us look at this E step a little carefully. So what this E step says is, and it can, because again, this E step can be a bit confusing and a lot of errors happen in this E step. To implement the E step, we need the conditional distribution of the unobserved data Z given the observed data X, right? So we need the distribution of the unobserved Z given the observed X. That is, we need to find the distribution f of z given x comma theta. So then so this is what I need. Now this might be a discrete distribution or a continuous distribution based on what the hidden data z represents. Then once I have this understanding of what z given x and theta look like, then q of theta given theta k is this expectation, which is then nothing but integral of log of the complete log likelihood times whatever is the distribution with which with respect to which I'm taking the expectation, which is f of z given x comma theta k. So and then this is integral with respect to again dvz, where this dvz again over here denotes summation or integral or integration. Okay, right? So what I want to highlight here is that this part has theta here and not theta k, and this part here has theta k. So as a function of theta is the parameter I want. Theta k is just a constant. It's just a current given value of the parameter, and it is a number, or it's a vector of numbers, right? So this part doesn't have theta in here, but this part has theta. And this is what I want you to make sure you remember. It is this part of the integration that dictates what the shape of this function looks like at different values of theta and how it changes over the parameter space. And it is this part that contributes then to the maximization. Of course, because your Q is an integral, the weights given to each of these values of theta is different based on what theta k is. So naturally, theta k has some input into what Q looks like. But what I want you to understand and make sure you process is that this is log of the complete log likelihood. Log of the complete likelihood for any given value of theta, and this is the conditional distribution of the unobserved given the observed at a particular value of theta. Okay. So in this way, the expression to the right over here is a function of theta given a particular value of theta k. And then in the nth step, I can maximize this function as a function of theta to get the next iteration theta k plus 1. Now, the following theorem that I'm going to talk about next is going to convince us that running the above algorithm, this E step and the M step, actually gives us a maximization solution. So we'll ensure that theta k converges to a local maxima, as the EM algorithm will turn out to be an instance of the MM algorithm. Okay, so that will be the next theorem. Now, the proof of the theorem I'm not going to go over in this video. It is, however, there in these very notes. So you can take a look at the proof of the theorem. I will just explain the proof very quickly as to what's going on, but not going to go into all the details. So you may skip the proof, although I have provided it here. So the theorem statement is very simple. The EM algorithm is an MM algorithm and thus has the ascent property. So let's recall what is the ascent property. So let's say I have my parameter space theta. So I have theta on the x-axis. Maybe I want to look at a slightly different function. So I have theta on the x-axis, and this is, let's say, my f of x given theta log, right? So this is my objective function, log of the observed likelihood. And this is my current value theta 0, let's say, or theta k. Then the ascent property says that in every iteration, I will most certainly climb the objective function, as in the next iteration will always take a value larger than where it is right now, larger than or equal to where it is right now. This is what we showed for the MM algorithm, that the MM algorithm indeed has this ascent property, right? And so EM algorithm turns out to also have this ascent property. And this is the theorem. Now, like I said, I'm not going to go through the proof of the theorem, but I'll go through a little bit part of it. So now, in order to show that this result, we need to first find a minorizing function. So what is an MM algorithm? An MM algorithm at any point constructs a minorizing function and then finds the maximizer of that minorizing function, and that maximizer becomes the next point. Then it creates a minorizing function again and finds the maximizer of the minorizing function. Okay, so to show that the EM algorithm is an MM algorithm, I first need to find a minorizing function and somehow connect it to our current EM algorithm. Now, let's recall that the objective function is log of f of x given theta, log of the observed likelihood. So what we need to do is we need to find, in the notation of the MM algorithm, a function f tilde theta given theta k, a minorizing function, such that f tilde theta k given theta k, as in the value of the minorizing function at theta k, is exactly the target for objective function, which is log f of x given theta, as in the minorizing function must agree at the current value of theta, right? The minorizing function must touch at the current value of theta my objective function, and everywhere else it should be bounded above by my objective function. So f tilde theta given theta k must be bounded above, must always lie above my objective function. And what the proof of this theorem depends on is to show that one such minorizing function, f tilde theta given theta k, is such that f tilde theta given theta k is q theta given theta k plus some constants. So what is this q? This q is nothing but our E step, right? And so what we show is that the E step function q plus some constants is nothing but a minorizing function, which means that so the first half of the proof tries to show this, that there is an f tilde that I can construct by just adding some constants to q that shows that f tilde is a minorizing function. And that's what this whole part of the proof relies on that. Okay. So I'm skipping these details. If you're curious, please feel free to read them. They're more or less self-explanatory, this proof. Okay. Now, once I show over here, I show that f tilde theta given theta k is a minorizing function. Now, according to the EM algorithm, the next iteration theta k plus 1 is found by maximizing f tilde. Right? And so I want to maximize f tilde, but f tilde is nothing but q theta given theta k plus some constants that don't depend on theta, which means now maximizing this as a function of theta is equivalent to maximizing just q. So the argument that maximizes f tilde is exactly the argument that maximizes q. So q theta plus 1, it can just be obtained by maximizing q theta given theta k, which is exactly the m step of my EM algorithm. Which means that if I do the E and the M step of the EM algorithm, I'm essentially doing an MM algorithm. And hence I have the ascent property as well. Okay. So this is the structure of the EM algorithm. These are the two steps that one needs to do in order to implement the EM algorithm. And as it turns out, the most tricky part often is just ensuring availability of this expectation. You can understand that this expectation can be a little bit complicated because it is integral log of f of x comma z given theta times f of z given x comma theta, and I have to have this available to me, which can be a little bit challenging to see how that might happen. So what we'll do in the next video is we'll go over one really popular and very powerful implementation of the EM algorithm through an example which is on the Gaussian Mixture Models. And this turns out to be probably one of the sort of most interesting parts, most interesting models that you're going to learn about in this particular course. So that comes up in the next video.